We go to example 12.2, right? So here you have a simply supported beam, which means that one is pin and one is roller, okay? Roller supported. And then you have a triangular load, okay? With the peak load here is W node, alright? Distributed load by the way, okay? And then this symmetrical about this in the middle, okay? So this L equal to L over 2 and L equal 2, and this is symmetrical left and right, right? So the question asks you to find what is the maximum deflection. I mean, let's say the question asks you to find what is the equation of symmetrical. So basically, if you want to find what is the maximum deflection, you need to find out what is the equation of elastic curve. Alright, first. So as you can see here, actually you have to do two cuts, right? One here and another one here. The reason is because from here to here you have a certain condition. I mean, if you cut and you see your V or M and M, you will see that you will have the same V and M, okay, throughout. But once you pass this X equal to L over 2 in the middle, okay, you cut and then you will see it differently. I mean, you will need to take either left or right, but if you take right, then the V and M will be different, alright, from the one that you cut here. But because in this case, well, I said actually you need two cuts, okay, but because here actually it is symmetrical, you can exploit the symmetry of this problem, which means that if you cut, for instance, on the left, you just take here, for instance, the left hand side, because it's quite foolish to take the right hand side, right? In this case, you take the left hand side, and then whatever happened here, it will just be mirrored for the other side. Alright, that's what it means by symmetrical. Okay, so let's cut. Let's cut and see. When you cut, okay, by the way, I forgot to mention, before you do any cut section method, basically you need to do this first. Alright, what do you need to do? You need to find the supports, right? So what are the equivalent supports here? Because once you cut later on, okay, let me draw it for, okay, you will have this distributed load. This is not W node, okay, the node in the middle. You cut it somewhere, so it is, let's say, whatever name you want to call it, W for instance, okay, WX for instance. And then you cut here, you will have your V, internal shear force, and internal bending moment M, okay, M and V, and then this is your X, right? And this is the point. And here you need this reaction. Alright, so before you cut, find the reactions. In this case, do the free body diagrams. I mean, find the equivalent loads, okay, for this distributed load on the left hand side, right hand side, and then find the equivalent, and they will be equal, by the way, and this magnitude will be W naught L over 4. This is not magic, try to find it your own, okay? So this one, it is W naught L over 4. Okay, L over 4, okay? So this is your distributed load W. W naught L over 4, at this point you cut, you have, at the section that you cut, you have the internal bending moment, internal shear force V and internal bending moment M, okay? And then X from X equal 0 to X equal to L over 2, okay? I mean, here L over 2 is X generally. And then what do you have here? WX here. So this WX, okay, you need to express this. It's not W naught, okay? W naught is the magnitude, the maximum magnitude, which is this. WX is somewhere here. I mean, okay. So what you have to do to find this WX? You need to find what is the equivalent, okay? So the method here is look at the whole triangle of distributed load. Okay, okay. This is W equals 0. This is W naught, right? W0, W naught, right? You take the triangle. Can you see that this is X? Okay, because you cut, and this is X, right? So this is your WX. Okay, and then what is this? Total length. It is L over 2. Okay. So if you take, for instance, let's say you take theta or whatever method of equal triangle, basically if you take theta, you will have, for instance, you say the tangent theta, it is, you have two triangles, right? One small in the triangle and the big triangle outside. So if you take tangent theta, you will get WX over X equals to W over L over 2. Okay, follow me. Tangent theta, WX over X equals to, and tangent as well for the big triangle is W naught over L over 2. Alright, so your WX is 2 W naught 2 W naught X over L. Okay, so your WX here is 2 W naught X over L. Right? Is it WX over X? W over L over 2. So W equals to W naught X 2. Okay? Okay, so after you found that one, you need to find, this is the distributed load, okay? This magnitude of distributed load at this point. So again, if you want to do this, you still need to find what is the equivalent. Okay, the one which actually, if you do the Fibonacci diagram for the whole, you need to find what is the equivalent. Okay, equivalent. So do you find this equivalent concentrated load? It is actually this area, right? So it is, okay, this one. The area of this triangle is W naught, W, which is 2 W naught X over L, isn't it? Okay, times X, okay, divided by 2. Alright? So this concentrated load is in fact, it is W naught X squared over L. Alright? So, okay, we follow with, just do the moment about this point, right? And then you will have your M, okay, M plus this constant equivalent concentrated load, which is W naught X squared over L, right? Times, okay, what is this distance? Okay, what is the distance? It is 1/3 of X. Please know this. Equivalent distributed load of triangle is 1/3 from the big side. Okay, so this is X, so this is 1/3 over X, this is 2/3 over X. So this is 1/3 of X, right? And then you have this one, which is minus W naught L over 4 times, what is the distance? The arm, it is X to 0. Right, so your M is, you solve this, so your M will be minus W naught L, sorry, minus W naught X cubic, okay, over 3L plus W naught L over 4X. Okay, solve this, okay, bring it to the other side, and then you will get this M equals to such expression, right? And then now we go to the equation over there. Because you have M, you start with this second derivative. So it is EI second derivative, okay, equals to minus W naught X cubic over 3L plus W naught LX over 4. Okay, because this is M. So you integrate once to get the slope, right? So now it becomes the first derivative. From the second derivative, it becomes first derivative. Okay, and this is the slope. So you integrate this, you get minus W naught X power 4. 4 times 3 is 12L. So this one you have the C1, right? Plus W naught L X squared over L, and you got C2. Oh, sorry, not C1. This one and this one plus C1, right? Sorry, my bad. Right? And then you have to integrate one more time to get the deflection. Okay, this is the slope. So you will have your nu, which is the deflection, and then you will have here W naught X5 over 60L plus W naught L X cube over 24 plus C1X plus C2. Alright? So you left with two constants, C1 and C2. Okay? So what you have to do, you have to find what are the integration constants C1 and C2. Again, put the boundary conditions. Okay, I believe you can just erase this. What are your boundary conditions in this case? Boundary conditions. What do you have? At x equals to 0, which is this point, right? You have 0 deflection, isn't it? So at x equals to 0, you have nu equals to 0. okay, at this point, because it is roller supported, isn't it? So it doesn't move, doesn't have deflection at this x equals to 0. That's one. And then the one is at x equals to L over 2, which is in the middle here. What do you have? You have maximum deflection, okay? You have maximum deflection, but because it's symmetrical and you have maximum deflection over there, you will have slope here 0, which means that the theta or d nu over dx equals to 0. Okay, so you can put these two boundary conditions and then you will get your unknowns. Integration constants. You put over here the first one x equal to 0, okay, x equal to 0, nu equals to 0. So your C2 is 0. Okay, this is your first integration constant. Right? And you put x equals to L over 2 over here. Well, you get your d nu over dx equal to 0, okay, L over 2, and then you will get your C1. So basically you have d nu over dx equal to 0, and then you have minus w naught x equals to L over 2, isn't it? Power of 4, alright, over 12L, plus, I hope you can see this, w naught L over 2, okay, x equal to L over 2, squared over 8 plus C1. So you solve this, you will get your C1 equals to minus 5 W naught L cubic over 192. Alright? So finally, you put these two constants, C2 equals 0 and C1 equals to this into the this equation, which is the elastic curve, right? So you have your elastic curve equation as mu as function of x, let's put it that way to make it better, 1 over EI, okay? You have this W naught x power of 5 over 60L plus W naught L over 24 x cubic is 5 plus C1x, so minus 5 W naught L cubic over 192 x and plus C2, which is 0. Okay, so this is your equation of elastic curve, right? So if the question asks you to find what is the maximum deflection at x equal to L over 2 in the middle, right? So you just put x equals to L over 2 here, and then you will get your maximum deflection, okay, from this point to